Today is 28th Feb is celebrated as a National Science Day to commemorate the discovery of Raman effect. This effect was given by Sir C.V. Raman, who was an Indian physicist, जिन्होंने physics के field में immense contribution किया है, and he also won Nobel Prize for the same. So as to celebrate this day, इस special occasion पे science talk रखी है, and आज के guest हैं हमारे Mr. हर्ष प्रताप सिंह, जो कि phase space dynamics पे एक talk present करेंगे. हर्ष currently IIT दिल्ली से मास्टर्स फिजिक्स के स्टूडेंट हैं, एंड इन्होंने नेशनल एक्सपेरिमेंटल स्किल टेस्ट में इंडिया में टॉप किया है. सो आई वेलकम हर्ष टू स्टार्ट दिस प्रेजेंटेशन.
Okay, so first of all, I want to thank Ms. Sanchita Singh for giving me an opportunity to represent myself and basically to present on a topic named phase-space dynamics. So I will use the classical approach in this particular talk. And so let us move on to the presentation. So the topic is phase-space dynamics. So it is basically describing the particle's dynamics in the space where we use to describe the coordinate and the velocity of the particle. So phase is a term. So basically, just one second. So basically we are having a term phase here. So that describes the velocity of the particle. So when we multiply it by mass, then we'll get momentum. And it is nothing but these are the same things with a proportionality factor of mass only. So we are basically plotting the trajectory of the particle on a plane, which is represented by the position x of the particle and the momentum p of the particle. So why this is useful? That first of all, the question arises why we are using phase space to represent the dynamics of a particle. Why not we are using the coordinate space in which we are usually having the x, y axis in general. So the reason behind this is simpler, and the reason behind this is very basic, that we have to basically find the dynamics of the particle without solving the conventional Newtonian equation. I mean the F is equal to ma. So in this equation, this acceleration term is basically the second order derivative of the position. So this creates some problem while the potential are very complex. So in case of some special potentials or some complicated potentials, when we solve this equation, we will get two constant of motion. And so to get those two constant of motion, we have to impose two initial condition. The first condition is the velocity at some zero time, and the another one is the basically position at zero time. So to deal with this particular problem, we have to find out these two things to predict the dynamics of the particle. So if we use the phase space initially, then we will get these two things on the same point. I mean, if we are using the phase plane, then we will get the velocity and the position at some initial time on a single point, and that unique point represents the initial point, position of the particle. So this particular phase space, the XP diagram, that is basically representing the unique point which is describing the particle phase at a particular time t. So the evolution of that is basically given by the Newtonian equation, that is our usual equation. And so the most advantageous point is that we can predict the particle dynamics by only getting the energy of the particle, I mean the Hamiltonian. So basically in classical mechanics, we used to define Hamiltonian as the sum of kinetic and potential energy. And that is the case for when the potential is independent of, when basically the potential is independent of the generalized velocity term. So in that case, there is no dissipation in the system. So that's why we can represent Hamiltonian as the total energy. So by using this Hamiltonian, we can plot this phase-space trajectory, and we can get basically the dynamics of the particle. Now moving on to the next slide. So now this is the introduction. This is a basic introduction to phase space. So in dynamical system theories, first of all, basically this is a different kind of theory. Let me describe the approaches we used to have in classical mechanics. So basically in the first approach, we use Newtonian mechanics. In the second approach, we used to have just one second. We used to have Lagrangian mechanics, and in the another approach, we used to have the Hamiltonian mechanics. So why we are using these three approaches there, just to deal with the problem, like to make the mathematics simple, we use these three approaches. So in the first case, that is very simpler case. So for the simple problems like oscillating spring and a ball falling on earth and some kind of these type of problems, we can use the Newtonian mechanics. And if we are having like very hard problems, suppose we are having a problem in which we are having a double pendulum, so the dynamics becomes more complicated, and that's why we shift to the energy approach. So in that case, we first write down the Lagrangian, that is given by T minus V, and so then we use the Lagrangian equation of motion, and so on and so forth. Then we will get the dynamics of the particle. So this particular phase space approach is based on the Hamiltonian mechanics. So that is the more advantageous point, is that the Hamilton's equation of motion are first order. Basically, Q dot is equal to del H over del P, and P dot is equal to minus del H over del Q. These two equations are known as Hamilton's equation of motion. We can also write them in Poisson bracket form, and that looks more symmetrical also. So basically, these Hamilton equations are predicting the dynamics of the particle in phase space. So these are first order equation. So it is always easier to solve first order equation rather than using a second order equation, which is our basically the Newtonian equation mx double dot is equal to f. So solving that is a cumbersome task for the complicated problems. Okay, so that is basically the advantage of this phase space approach on the Newtonian mechanics, so Newtonian approach. So now this is basically a simple phase plane, and I am representing the velocity, or basically we can correspondingly call this axis as the momentum, with the position of the particle, which is representing as q. Why I am representing it with q? Because I am describing it as a generalized position. So basically basically it can be some angular position of the object, or here we can get the angular momentum for that. Basically we are in canonical conjugate. So for angular coordinate we are having angular momentum, for linear coordinate x we are having basically the linear momentum p, and so on and so forth. So like for the time case we are having energy as the canonical variable. So in this way, one more thing I want to emphasize here is that we can relate this thing with the quantum mechanics also. So in quantum mechanics we do not have phase space, but we are having a similar kind of thing which is called as Hilbert space in quantum mechanics. So now the more beautiful aspect here is that to know the dynamics of the particle in phase space, we have to know only two things, like the position at 0 time and the velocity at 0 time. But to know the dynamics of the particle in quantum mechanics, we have to know the wave function psi x of the particle, which is a continuous parameter. So we have to basically know the initial condition of the particle at each and every point in this Hilbert space. So that is the basic difference in the formulation of classical and quantum mechanics on the basis of this phase space and Hilbert space. So this is just a representation, and this is basically the time evolution of a state in phase space. So that is basically given by the Hamiltonian, because we are defining Hamiltonian as the generator of time evolution of a state in phase space. In quantum mechanics, similarly, we are having an operator used for minus iota ht by h cross, and that is called as time evolution operator. That's a unitary operator. For sure, it is representing the canonical transformation, and canonical transformation are basically the transformation in the phase space. Basically, these are the transformation from one point to another point, and representing the particle position and velocity as a function of time. Okay, so now 1D motion of a particle under simple harmonic potential. That's my first case. So I am taking firstly the potential which is simple harmonic, that is Vx is equal to half m omega square x square. Most of you are familiar with this potential, and the equation, Newtonian equation of motion for this is also well known. That is basically x double dot is equal to minus omega square x, and that is our simple harmonic motion equation. So solving that is also not very difficult, because you can apply the Cauchy-Euler, and it can be simply solved because it is having some constant coefficients. And but in using this phase space dynamics approach, you can directly predict the dynamics of the particle by writing the Hamiltonian of that. So let me write out the Hamiltonian for this. It is p square over 2m, and we are having plus half m omega square. So if I want to find out the trajectory for this Hamiltonian, then this will be an ellipse. We can rearrange this equation. Let me show you the rearranged part. Okay, so this is our rearranged equation. So that particular, because Hamiltonian is constant here, that is the total energy. And for the conservative system, because I initially said that potential is not dependent on the generalized velocity, so we are taking the system with constant energy. So in that case, we can rewrite that equation in this form, and this form is basically the equation of an ellipse in the position and momentum space. So these represent some ellipses. I'm sorry for the diagram, and these are, but please assume these are the ellipses. Okay, so basically this is our potential. And here I am taking the energy of the particle to be positive in this case. So the more better interpretation we can get by analyzing this particular potential. So suppose we are having some points plus a and minus a corresponding to these energies. So what we will describe is that only this region is allowed for the particle to oscillate. That's why this is bounded particle classically also. And I'm talking about the classical physics only. For quantum mechanics, there is some probability of getting the particle outside this classically forbidden. In the classically forbidden region also. And why this is outer region, why it is called as classically forbidden? This is because the potential is basically greater than energy. For the values above this energy. So that is not possible, because that makes the kinetic energy to be negative, which is not classically possible. So basically this region is forbidden for a classical particle, and same here. So only minus a to plus a region is allowed for the particle to oscillate, and that's why it's a bounded motion. And a bounded motion in a phase space trajectory is the closed curve. And here these are ellipses. So that is shown by the equation of basically when we write the Hamiltonian, rearrange that equation represents this ellipse. Okay. So that is a simple simulation that I am using to describe the phase space dynamics of a particle performing the simple harmonic motion. So this is the configuration space, the blue particle in the bottom side, that is representing the simple harmonic motion in configurational space, and the yellow particle is representing the same motion in the phase space. So we can basically find out the position and the corresponding momentum that describes the initial phase of the particle by simply writing the Hamiltonian. So that's the most beautiful thing about this approach, the Hamiltonian approach. Okay. So now this is another example, and it's also simulation. So here you can see the phase space trajectory of this particular oscillating spring that is also performing a simple harmonic motion, that is lying on the position axis, and its center is basically lying at some distance on the position axis. That is because there is some initial displacement already present there in this spring, that is mg by k. When you like balance these kx and mg, and then you will get some initial displacement already. So that shifts the origin, basically that shifts the origin on the position axis, and that's why this ellipse is slightly shifted from origin. That is the phase space trajectory of this oscillating spring. Okay. Now moving on to the next case, and nextly I'm taking this inverted parabola potential, and simply it is nothing but Vx is equal to minus half m omega square x square. That is just the opposite of the simple harmonic oscillator potential. So in that case we are having a plus here, but this switch of a sign makes quite huge difference in these two things. You will see that the phase space dynamics of this particle is an ellipse, that is a bounded one, but here the phase space dynamics will not going to be a bounded one. It will be in kind of hyperbola. It will come out to be hyperbola. So okay, let us write down the Hamiltonian for this system. That is p square over 2m and minus half m omega square x square. Okay, so this is basically our total energy, which is constant for a conservative system, and we are assuming conservative system here only. So this for basically momentum and position These represent the equation of a hyperbola. So if we put x is equal to 0, we will get p to be basically p will come out to be plus minus under root 2 me. So that describes the 2 points on this phase space. Let me represent these points. So this is something of this kind. And when we put basically p is equal to 0, then the point come out to be this. So this kind of phase space trajectory is there for the particle. So it will not going to reach the origin, and it is not a bounded motion. You can see this is extending up to infinity. So that is an open kind of motion. And okay, so let us discuss the forbidden region also in this case. So this is our inverted parabolic potential in this one. Okay, so that is an unstable equilibrium point, and for the basically harmonic potential, we are having this one as stable equilibrium point. Okay, just one second. So this is our equilibrium stable equilibrium point, and this for the inverted potential case, this is our unstable equilibrium point, because if you displace the particle on this side slightly, then it will go on that side. It will not going to come back. So that is why it is called as unstable equilibrium point. Okay, and you can also show it by basically del v by del x. That is kind of thing. When you put it equal to 0, it gives the condition of extremum, and then you will check by del square v by del x square. If it is greater than 0, then that will give you minima, or less than 0, that will give you maxima. So that is also approach. So here I have represented the trajectory, phase space trajectory of the particle for the different cases. So these straight lines are representing for energy equivalent to this is representing for energy equivalent to 0, because that will represent a straight line on phase space trajectory. You can check by putting E is equal to 0 in this particular expression. So you will get p square by 2m, that is equivalent to half m omega square x square. So by taking square root on both sides, you will get a linear equation in x and p. So that represents a straight line. So that is why for energy, zero energy, this is a straight line. And we will not join it in the center because it is saddle point. Saddle point corresponds to this unstable equilibrium point. So that is the case. And these already we have seen how this is coming out. This we have already seen. For by putting x is equal to 0, we will get this kind for energy greater than 0, and for energy less than 0, we will get these kind of hyperbolic trajectories. So this is basically the phase space trajectory of the particle moving in inverted parabolic potential. Okay, so now a phase portrait of a bouncing ball considering Earth as a rigid sphere. So this is the third case. This is the third case. I have taken some simpler cases so to show the analogy we can establish between the Newtonian approach and this phase space dynamics approach. Okay, so for this the potential will look like of this kind. It's a linear one because v is equal to mgx. That's the kind of potential for a bouncing ball on the surface of the Earth. So it cannot penetrate it cannot penetrate this surface of the Earth. That's why we are not taking it on the negative side. So we are taking it just on the positive axis. Okay. So I'm putting some marks here so as to represent that there is no potential in this negative x region. Okay. So this is the phase portrait of a bouncing ball on the Earth's surface. So there's a discontinuity here. The phase space trajectories are moving like this, and there's a discontinuity present here. That is for the momentum, because when ball strikes the surface, then it rebounds, and when it rebounds, there is a change. Basically, there is an impart of momentum, and there is a discontinuity in this on this momentum axis. There's a momentum basically velocity or momentum axis. So that is the same one for the phase space, and this is our position axis. I mean the velocity and the momentum. Okay. So here we are having the discontinuity in momentum. That is the ball bouncing on the surface of the Earth, and that is basically the phase portrait. Okay. Okay, then moving on to the next case, the phase space trajectory of a particle in a damped harmonic oscillator. Okay, that's a different case. So here there's some dissipation kind of stuff coming. So the equation of a particle in a damped harmonic oscillator is given by something like x double dot plus gamma x dot and plus omega naught square x. So that's the simple equation of motion for a damped harmonic oscillator, where gamma is damping factor, omega naught is natural frequency of the oscillation. So in this case, the phase portrait will going to will show kind of damping. Let me show the phase space diagram for this. This is the phase space diagram. So it is showing some kind of damping. You see, like it is the particle phase is moving inside, and you see it is dropping down time by time. It is dropping down. When you move inside, it will drop down to basically almost zero level here, because energy is decreasing now, because energy is not constant here. For if you represent it for the 1D simple harmonic motion case, then p square by 2m and plus half m omega square x square. So that is in this particular potential, there is term which is going to represent the damped oscillation. So that's why it is basically dropping down to 0. Okay, thank you. That's all. Hello. You're not audible. Hello.
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 I'm saying that you can now stop sharing this.
Okay.
Thank you so much. And अगर नेशनल साइंस डे के ओकेजन पे कुछ एक्स्ट्रा ऐड करना है, बोलना है.
Okay, so basically, first of all, we have to look science not as a part of a syllabus or curriculum. We have to look more for science. Like basically, science is the way to live. It is like a coconut kind of stuff. So if you dig inside, then you will get the taste of it. Otherwise, if you touch the surface only, then you will not going to get the real feel for the science. So that is the case. Like we have to enjoy science, not basically accept it as a part of a syllabus or curriculum. That will always make it going. Yeah.
So thank you so so much and very happy National Science Day to everyone once again. तो इसके साथ आज का presentation end करते हैं आज की talk. Thank you so much.
Thank you so much, Sanchita. Thank you.